Scientists have a unique approach to studying things. It's often called the scientific method. And it was actually very important development historically compared to the philosophers, the people who sat around thinking about why is the world the way it is. Scientists don't just think about it, we actually do stuff. So the scientific method involves understanding nature by observing its behavior and conducting experiments or tests to see if our ideas are correct or not. The main characteristics are observation, formulation of hypotheses, experimentation, and formulation of laws and theories. And we'll talk about each of those individually. So observations are also called data. These can be numerical, the mass of something, or they can be qualitative, the color, the smell, the feel of something. But collectively it's called data. The descriptions of the characteristics or descriptions of the behavior of nature. And observation is what often leads us to a hypothesis. So the example given in your book are some experiments done by Antoine Lavoisier, who's a French scientist who lived back in the 1700s. I'm going to tell you about some famous scientists of the past. I'm not going to quiz you on their names or the dates of their birth. I think it's just kind of nice to remember some of these people. So he noticed that there was no change in the total mass of material within a container during combustion. What does that mean? He was interested in what happens when you burn things. I don't know about you, but even as a small child, I was always fascinated by fire, right? And my kids are that way too. And I think, honestly, all chemists are secret pyromaniacs. We enjoy burning stuff up, right? I'm cautious. I don't want to blow myself up, but I love playing with fire. So he took a closed container and burned stuff in the closed container. He weighed it before, he weighed it after. And what he observed was that the container with the stuff in it weighed the same before he burned it as it did after he burned it. What do you know about the mass of a fireplace log? You put a big log in the fireplace and you burn it, you have a nice fire in your fireplace. Afterwards, does the log weigh more, less, or the same as it did before? It weighs less, right? Do you ever think about what happened to the rest of it? Where did it go? It went up the chimney, most of it. But back in the 1700s, people didn't understand what happened during combustion. So he weighed it in a closed container before and after. So this was his observation. The observation leads to a hypothesis. Why? What's going on? What's the explanation for what I have observed? So a hypothesis is a tentative interpretation or explanation of our observations. So he explained this observation by hypothesizing that when a substance burns, it combines with a component of air. So he had whatever it was he was burning in there was air in there, and it was combining with something in the air. That was his hypothesis. One characteristic of a good hypothesis is that it is falsifiable. You could test it and possibly prove it wrong. You know, you can't test a hypothesis that invisible space aliens are coming into the container while it's burning and doing magic. Well, that's a hypothesis, but how do you test that? You can't test that. It has to be something that you can test. So we test hypotheses by experiments. These are controlled procedures. We set up a very controlled environment and we see, well, if this is true, if my hypothesis is true, then when I do this, this should happen. And then we do it and we see what happens. And the results can support the hypothesis, or they can say, no, your hypothesis is wrong. If your hypothesis is wrong, you can either throw it out and start over again, if it seems like it was really awful, or sometimes you just need to modify it a little bit. So Lavoisier's original hypothesis about the substance combining with something in the air turned out to be wrong. Well, I'm sorry. It does combine with the oxygen in the air. There was this whole business of the phlogiston. And if you're interested in that, you can read about it in the book. The idea of the phlogiston, this mysterious substance in the air, that was pretty wacky. But it does combine with oxygen in the air. So you test the hypothesis, and if it turns out that your hypothesis was correct, then usually it gets tested again and again. Scientists are curious, and we're pretty skeptical about what other people do. We want to see it for ourselves. So if you tell other people about your hypothesis that you confirmed, they're going to think, well, I'm not sure I believe that. I want to try it myself. And so other scientists will replicate your experiments to test your hypothesis, maybe come up with some new experiments to test your hypothesis. So after much testing, we can come to scientific laws and scientific theories. And there's an important difference between them. So a scientific law is a brief statement that summarizes past observations. It says this is what happens. Doesn't explain why, but it says this is what happens. And it predicts future ones. From Lavoisier's experiments came the law of conservation of mass, that in a chemical reaction, matter is neither created nor destroyed. And as one of the students over here pointed out, when you burn a log in a fireplace, the mass doesn't disappear, but the substances in the wood are combining with oxygen in the air, and they're forming gases, specifically water vapor and carbon dioxide, and those gases go up the chimney, and what's left weighs less. But if you burn it in a closed container, you observe that the mass has not changed. You can't destroy or create matter just with a chemical reaction. This allows us to predict future observations. Based on this law, we can say, well, if I react these two things, the mass overall is not going to change. One important thing about laws, scientific laws, you can't choose to violate them. State laws, federal laws, you can choose to disobey those laws, right? You can choose to speed on the highway. You may pay the consequences for it, but you can do it. You cannot disobey scientific laws. You're familiar with the law of gravity, right? So if I hold out this Sharpie marker and I let go of it, what does the law of gravity predict is going to happen? It's going to fall to the ground. Sure enough, every single semester it does that. Does the law of gravity explain why it does that? No, it just says that it will. And you can't violate the law of gravity, much as you might want to. A theory comes about when you have one or more well-established hypotheses. And this is where other scientists have jumped in and tested this same hypothesis, and nobody can find a test that proves it wrong. Then we accept that as truth until we learn more. This is a scientific theory. John Dalton, who lived in the 17 and 1800s, so after Lavoisier, he came up with the atomic theory that explains the law of conservation of mass. Law of conservation of mass says what happens. Atomic theory explains why. It proposed that matter is composed of small, indestructible particles called atoms. So when you have a chemical reaction like wood burning, the atoms get rearranged into different substances, but they don't get destroyed. I use a lot of analogies in my lectures, and one of the analogies I've found useful is atoms are like Lego blocks. Okay, so all of you at least know what Legos are. I should bring a picture of the Legos at my house. We've been collecting Legos for about 20 years, and we have quite an extensive collection. But individual Lego bricks, can you break those with your hands? Some of the long, skinny ones maybe you could, but I'm talking about the regular little bricks, the 2x2s and the 2x4s. You can't break those with your hands. They're pretty sturdy. You can put them together in different ways. You can take them apart. But the Lego bricks themselves do not get created or destroyed. And so that's how atoms are. When we're having a chemical reaction, the Lego blocks are getting rearranged. And it may look like something completely different. You may start out with a spaceship and end up with a giraffe. Right? But the blocks themselves are the same. The atoms themselves are the same. So a scientific theory, then, is a model for the way nature is. We're trying to explain nature, why it is the way it is and how it works. And it tries to explain not merely what it does, but why. Why do these things combine in the way that they do? And so that's what a theory does. Theories are validated by experiments. We can never conclusively prove something to be true. And that's a concept that bothers students sometimes. What do you mean you can't prove it to be true? We can't. I mean, in a philosophy class, they can get you going on, prove that you exist, right? Think about that one for a while. How can you prove that anything exists? You can't, really. You have to make some assumptions. But we can't prove that theories are true. All we can do is say, nobody has come up with an experiment that disproves this theory yet. And we'll mention some theories as we go along through the course that have been revised. As we've made new discoveries, we've realized that the old theory wasn't quite right. And so we can fix them. Theories are great because they explain, and they can be used to predict future observations. A well-established theory is about as close to truth as you can get. Sometimes you'll hear people say, oh, well, that's just a theory. Well, maybe in everyday life, a theory doesn't mean much. But in science, a theory is a very significant thing. It's not just a theory. It's a theory. This has been tested by lots and lots of people. It's as close to truth as we can get. Sometimes we get the idea that science is this rigid set of rules and procedures, and you do this, and you do this, and you go through these steps, and you come to the end, and it's all nice and neat. It isn't. The actual practice of science is very messy. But that messiness actually is a lot of the interesting part of science. It's not like adding up columns of figures to keep the books for your farm, where you add things up and that's just it. You have an observation, you test it, and sometimes in the testing of it, you make some new observations that just change everything. And so you end up kind of going in circles. So here you have observation, and from the observation, you have a hypothesis. From the hypothesis, you do some experiments, you test it. So if the experiment confirms the hypothesis, then that's great. If you disprove the hypothesis, then you come back and you revise it. And sometimes you go around in this little loop here for quite a while before you come up with a hypothesis that you can't prove wrong. The hypothesis that is confirmed over and over becomes a theory. Theories are also subject to ongoing testing through experiment, and so we get loops over here. And observations can lead to laws. Laws sometimes lead to hypotheses. Laws are also tested. Small boys are especially prone to testing the law of gravity. You know, put on a Superman cape and jump out of the tree, right? Oh, sorry, law of gravity still works. You're not going to fly. So here's a question. Which of these statements best explains the difference between a law and a theory? So statement A, a law is truth, where a theory is mere speculation. Does that sound like a good answer? No. A law summarizes a series of related observations, while a theory gives the underlying reasons for them. Is that a possibility? That sounds pretty good. Let's check the last one. A theory describes what nature does. A law describes why nature does it. No, that one's exactly backwards, isn't it?
Right.
So the correct answer there is C. I'm sorry, B. What am I saying? So this is the correct answer. Any questions?